We could start now. And warm welcome from our side, from my side. My name is Sven Blank. I work for the Composites United, especially for the department My Carbon, located in southern part of Germany. Today, we have 90 labs with a very interesting presentation today, and some rules before we can start with the event today. Please switch off the sound and the videos, and the Q&A session will after the event. Yes, 90 Labs is a very innovative company, and today Yannick and Martin both are have a great experience in the field of composites since years. And now we can start with a presentation, how additive manufacturing, continuous fibers and thermoplastics join forces for a new generation of serial structural parts. Wow, that's interesting. Yannick and Martin, the stage is yours. Have fun and see you after your presentation.
Thank you so much, Sven. Thanks for the introduction. Can you hear me okay? Just one final check before I get going.
Very clear, yeah.
Okay, great. So thanks for already also mentioning the title. I think it's a little bit different. It's not just focused purely on our approach, but also on a hybrid approach we will talk about in a second, but I don't want to take it away now. So first, Sven already mentioned our names and a little bit our background, but I just want to recap a little bit and just give you some extra information. Some of you, from what I see, already know us, but just so for the ones on the call that do not yet know us, Yannick, Willemin, very experienced in composites, has been with SGL Carbon for more than 15 years before I joined 90 Labs, with 90 Labs closing in on 3 years. So we already have some good history together, and yeah, very excited. He is heading our marketing business development efforts. He has been in various roles throughout his career, from technical to business development and management. And it's great working with him. My personal background is also mainly engineering. So I've been in fiber composites, also composite materials for almost 10 years. And in particular, started in my master's time, and then throughout my PhD time and at 90 Labs, then I continued that. So mainly on thermoplastic composites and continuous composites in the context of additive manufacturing. And yeah, it's a pleasure to be here. In my role as a CEO at the moment, I'm more like a sparring partner for commercial and technical teams. So let's jump into the presentation before we go into the actual agenda. Just quickly on the company itself. So we are an official spin-off from ETH Zurich, a little bit over closing in on a little bit over 4.5 years, closing in on 5 years in total. We have institutional investors and strategic investors backing us. We closed early this year, $17 million US Series A round. In total, we are a little bit over 20 million in funding, which is very much dedicated to developing the technology stack and also building out the commercial pipeline. And at the moment, we are closing in on 60 employees, and continuously building out not just the technology but also the team. Also in the US, that's why I'm for me, this is a little bit early this morning, this presentation, but we also opened an office in the US and getting traction here in the US on the commercial side. So let's jump into the agenda first. So here I will start off and give a short background on motivation and context for our technology. Then I introduce the technology on a higher level, and then I give it over to Yannick, who will take the core of this presentation, or present the core of this presentation, which is on the hybrid manufacturing with AFT. AFT is this additive fusion technology, which is our solution, which we'll talk about in a second. And he will also give some concrete examples on how to use this hybrid approach with our AFT solution. And then we have some concluding remarks, and then we go into a Q&A, as you are familiar with in webinar sessions. So feel free to ask as many questions as possible. we're happy to answer them. So let's get started. On the motivational side and the context side, I will have some introduction slides. I will go through them fairly quickly because most of you already have a good background on, or from what I see, like a good background, and also in the context of Composite United, a good background on composites. So what we need are better performing parts using significantly less resources. This is something we always state because this is like now detached from composites, first of all. But what we really need for the future is like better parts than we have right now, like across all the different applications, what we see all across all the different verticals, but using also significantly less resources. And one of the materials that is like very promising to deliver on that promise is continuous fibers, yes, but thermoplastic composites in particular. And in this group here, I don't want to go through all the different elements and highlighting the composites and what they have, because you have this background already. I just want to state that usually it's perceived a lot about lightweighting the part, and that's correct, but there are also other merits to the material than which a lot of people might not, or a lot of people outside of composites in particular, in the metal space in particular, do not necessarily know. So the X-ray radiolucency, that we have a high impact absorption capabilities of the thermoplastic composites, that we have a real chance to make a fully recycled, closed recycling loop. But also, like, there's something actually would be a good topic for another webinar. I would love to talk about this and dedicate an hour to this. But there is a real opportunity, in particular with our approach, to deliver on that promise of recycling and also bio-based materials. We have a higher design freedom, dimension stability, like low CTE coefficient. There are many different aspects to it. So what I really want to make the statement is like, this is a material that has the potential to really deliver on that statement, which I had before, making better parts with less resources. So what are we currently making out of composite materials? Not necessarily just like thermoplastic composites, but composites as a whole. There are a lot of different applications, but a lot of them are thin shell-like structures, and we have a lot of kind of pull-through profiles. So that's kind of the classic application parts which we have. There are always, like, there's always exceptions in other parts, but this is kind of like the standard parts which we have a lot right now in the industry. So a little bit provocatively put also, like, so what about all of those like smaller, intricate, thick, complex parts, like which are predominantly in metal still? And there's always exceptions to this, you know, but when it comes to a structural part that's complex, thick, it's predominantly in metal still. So what are or why is that? It's mainly to still like very expensive material. Like there's a lot of companies working on getting the material costs down, but at the end, it's not just the material cost, it's also the technology stack itself, which is fairly costly compared to other like metal, like other alternatives like metal. So it's very expensive still, and there is still also a lack of integration with software and having a full solution approach. In particular, also one of the things is like digital thread, like digital twin, like being fully capable of simulating the part in a digital environment before you actually have to do a lot of tests. So this kind of elements are easier for metal, or are, let's say, more sophisticated, more developed for metal. And that's why this is also another very big limiting factor. So what we need, and this is also a little bit like it's just a general statement, what is lacking is really like this automation part to drive down the costs, aside of that, you know, the material supplier is also getting down the cost of the material feedstock itself and the raw materials, but we also need this integration with software. And like to make a full solution, like a full suite. And that's something we'll also talk about today. So that's one of the key elements to open up a new applications which we could not reach with the current technology, the conventional technologies we have right now. So also here on this slide, a little bit provocatively put, additive manufacturing, 3D printing has huge potential to fill a gap in a way of this automation and software aspect, integration with software and the automation aspect. But it's easily pitched as like it will solve everything, you know, like this is like the full, like, you know, fully automated integrated software, but we can do everything. But in the way, if you take a close look, it's more than just like printing a part. And if we talk about real applications, And that's why I want to transition to this slide. So what does it really need to make a series production part, a structural part for metal substitution, for instance, that has real load carrying capabilities? And there's many different ways to do those frameworks, but here just one. There are technologies out there for continuous fiber composites and in general composites, also short fiber composites. And if we put them into perspective here in this chart, we see that there is like a group that adds continuous fibers in an additive manufacturing setting, like in a 3D printer, but it's mainly on like maybe slightly load carrying applications, but it's rather prototypes and non-structural applications. So this is this entire group around Markforged, Another Print, Desktop Metal, Continuous Composites. Arriva actually, just see like it's also a missing element there. Arriva has also, in a way, materials that are structural, but at the end, the parts that come out of it is nothing yet compared to a fully composite, which we use in industry as of today. And then we have the group of Stratasys, 3 Systems. There are some others which have low porosity, so good quality parts, but not really structural. And in general, the group on the left is more for prototyping because of the quality, the internal quality of the part. We put it here as high porosity, low porosity. Could be also surface finish. It could be interlaminar bonding. So there are other criteria you could add to this. But at the end, the bottom line is like, it needs a lot. It needs what we know here in this group from the composite industry. We need this kind of quality if we talk about an actual series production part. And that's more like on the right, what you see, Impossible Objects 45, they have good internal quality of the part, low porosity, but not much load carrying potential. And 90 Labs and Ares, we have a little bit different philosophy, different approach, but what we share is that we enable series production of load carrying applications for widespread adoption of metal substitution. That's our main goal. And we can talk more about this. So this just like to highlight that there is more than just printing to it. And I will talk more about this in a second. If we manage, and we are managing in applications already, to get not just like the automation and integration with software through additive manufacturing into the solution, but also the load carrying capabilities and the quality which you need for series production, there is a great market opportunity. And I don't want to talk too detailed about this. If there's a question, we can also deep dive, but there's a great opportunity for thermoplastic composites, which are already like growing in the composite space, and also focused mainly on not necessarily all on very large applications. I mean, there are also fuselage aerospace applications, but there are also a lot of smaller applications which they are targeting. So there's a great chunk of opportunity with our solution, which we can target. And there's also a great chunk of opportunity in the, let's say, metal substitution area, which we now highlighted here, the precision parts. And if we look deeper into the precision parts, there's like this high-end precision parts like medical, aerospace, recreational, automotive, electronics. So more like smaller, intricate, complex, usually also thick parts for composites, which have a great opportunity when it comes to from a commercial side. So we're talking about more than $50 billion opportunity. So that's why it's not just a nice technology solution and technology stack, like the entire additive composite space, but it also has great commercial opportunities. So how do we do it? Let me see here. Using 90 Labs additive fusion technology. So this is our technology suite or technology stack. And I will like quickly introduce now like this additive fusion technology. Some of you already heard this before. I will not dedicate too much time to it because I want to rather give it to Yannick, and he can talk about the hybrid approach. But nevertheless, I will make a proper introduction on our technology stack. So this is the full solution you see here, what we call the additive fusion technology. It has different pillars like software, the materials, the continuous fiber composite materials, 3D printing, and also the molding technology. So all the different elements are key to succeed in making structural series production parts. So in the software, you get really like this design capabilities to make optimized part, better lightweighting parts, but also like having the capabilities not just to simulate for making it more lightweight, also to validate, digitally validate the parts. So having a fully digital prototyping environment. But we'll talk more about this. Then continuous fiber materials, we're not just talking about adding some fibers, not short fibers, continuous fibers, but also like a lot of them. So we are talking about real structural performance. And what's also important that we don't reinvent the wheel on the material side, right? We want to have materials that have a proven track record that are known to industry. We'll talk about this in a second as well in more detail. 3D printing, key element, brings the automation, brings also the integration with software. At the same time, it also has like a significant impact on the CO2 footprint by not wasting a lot of material. In the conventional composite technologies, we are wasting a lot of material in the process, but there is like a real opportunity here to just print material where we need it. And at the very right, we see the molding aspect, which is a key element. So we're not just printing, we're also molding the parts. This is a key element to get all the final checkboxes for quality when it comes to surface finish, interlaminar bonding, porosities, but also gives a possibility to integrate with other materials like inserts, for instance, can be directly co-molded, and you can also add multiple parts together. And I will elaborate a little bit more on some slides to come. But this is the full solution, and it really needs all the different elements to really open up new applications. Just to highlight a little bit like how the software is structured. So we have something called Fiberfy Design Suite. This is our design software. It's a full CAD environment, direct model environment, where you can have a suite of tools on how to place the fibers, and we'll gradually also get more and more automated features into the suite. So I can also talk more into detail if there are questions. I just leave it like this for now for the introduction part. What's also important to understand, this environment has a direct link to commercial FEA tools. We work a lot with ANSYS, but there is also Abacus, Nestran environments which we can use to simulate the part. It's not just to necessarily optimize the part, also to digitally validate the part. Sometimes people forget that validation is also an important aspect, not just the optimization part. And we have another software suite or software component in our suite, which is Fiberfy Production. It's a cloud platform. It's connected to all the devices, so the hardware, and but it's also connected to the design software. So it's basically where all the data and the information comes together. Also the sensor data, the processing data, the log files, not just the design files. So that's important for a full solution. On the material side, here we have to understand that there are two materials, and I will talk on the next slide a little bit more in detail how to use it. There are two materials. We call it material pair. So there's one, it's either neat or short fiber reinforced filament or plastic, and the other one is a continuous fiber tape with a high fiber volume content. And what's important here to understand that we are using certified materials for regulated, that also can penetrate into regulated industries. In other words, like those are materials that are known to industry and have a proven track record. And you see some of them like PEEK, PEX, PPSs, the nylons, also other like PA11, like bio-based materials, and also the fiber is not necessary. We do a lot of carbon fiber right now, but we also not yet on a portfolio side, but on the R&D side, we also work with other material, other fiber reinforcements. So it could be glass, basalt, you name it, aramide. And the second main aspect of using this kind of approach, that we go for off-the-shelf materials, known materials, like the continuous fiber tapes, which are probably the only standard thermoplastic composite feedstock which we have in industry, is also important for the cost competitiveness. So that's, you see also our partners here on the bottom, Solvay, Arkema, Evonik. Those are some of the public partners which we work with on the different materials and on our portfolio. So when I talk structural, I really mean structural materials. So this is high fiber volume content materials. You see like the tensile strength is what you would know from the most structural fiber composite materials, 60% fiber volume content. So it's real composite. It's not just something like, oh, we added some of fiber and you have, I don't know, like 400 or 500 megapascal tensile strength. And it can outperform all metal materials, yes, but all in this group in particular, I guess we all understand that it's only good if we leverage the fiber and the strength of the material in the right way, right? Optimize the part. And this is maybe a good transition to this slide. So I mentioned in our solution, we leverage the software to design the part, and then we leverage the 3D printing technology to make this more optimized fiber design. And this looks different than most of the composite parts which we know, right? It has directed fibers, it has very intricate fiber orientation, local fiber orientation, curved fiber path. And what's important to understand that you have the continuous fiber strands, but you can also have the neat plastic or the short fiber reinforced plastic regions. And here in the small illustration example, you see like the green shaded areas are the continuous fiber paths. You see they're also curvilinear. We call this an omnidirectional fiber placement with our technology. And then the red areas, they are the neat or the short fiber reinforced areas. And this can also, like throughout the thickness of the part, it can vary, right? Because the fiber layup doesn't have to be the same fiber layer for each layer. So it could also kind of like be a very complex stack of this hybrid printing approach. So what it really means is like we can leverage the fibers, the fiber strength, and that's what we need to actually leverage the exceptional mechanical properties, which I talked before about. So one important aspect, and now we are talking about the fourth pillar in the introduction slide, where we had our solution, which is the molding aspect. The molding is important, has two main components. One is the quality, the other one is what I call the enlarging the design space, or yeah, we can talk more about this in the next slide. So here on the first slide, it's about quality. So it's about the internal quality of the part and also the external quality. So surface finish, you see here after printing, you still have the classic pattern on the side. You know, the surface finish has this kind of bead, like the like the washboard. I mean, in German we saw it like the washboard kind of pattern. And you see also that internally we have some voids, and then there is like porosity, and the interlaminar bonding is also not as good as what we know from an injection molding part, for instance. So after consolidation, it's a real molding process above TG, not just above TG, also usually close to melt temperature or above melt temperature. So we're really like remelting the part, co-consolidating the part all together. So there is perfect surface finish, what you would know from injection molding or molding in general. You would have perfect interlaminar bonding, and you have very low residual void content in the part, which we're always shooting usually for below 1% void content in the part. So that's a quality aspect, very important for serious production, getting into serious production and real metal substitution. But the other aspect is also that the molding enables us to make new things, have an enlarged design latitude. Or we can just like do new designs, designs we could not do before. So one is like that we bring in a software, we split an application apart into sub pieces, which are optimized, and then they come together in the molding, and then they're co-welded or co-consolidated together. And this enables us to do applications like this hinge, which we show a lot, which you cannot do with conventional means, because you have fibers that penetrate from vertical plate into the bottom plate. You know, they're kind of intertwined and interlooped, and this is what we can achieve by this multi-part assembly approach. We can also directly integrate inserts and other materials into the part, co-mold them in. But what we also can do on the right is we can reshape and deform parts in the molding as well. So this is like the introduction. I will just quickly now summarize the workflow, how it works. So we go into design software where you create the part, design the part, then you manufacture the preform in the printer. It could be also multiple preforms, as you see here. This is like for a Vertebra Winglet application. Then you bring them into the molds, into the fusion module, as we call it. Fusion module is where the molding device, where it co-consolidates to the final part. So this is the workflow. We have a short video to also show, and then I would give it over to Yannick, and he can introduce the hybrid approach in this AFT context. I will give it to Yannick. I'm not sure if you can still see it.
I'm sharing it now. It's fine. Thank you, Martin. Now we will just play a short video, and then I will move forward.
Additive fusion workflow offers a simple and cost-effective way to design and manufacture functional composites. Design even your most advanced part with 9T Labs Fibrify software. For the first time, true 3D fiber orientation allows you to design applications which haven't been possible to manufacture in composites before. Our unique software platform links with your commercial simulation tool of choice. This simulation allows you to validate the optimal part design and greatly speeds up your product development time. On the shop floor, our integrated cloud software acts as your manufacturing execution system. 9T Labs technology lets you produce parts that are 10 times stronger than metal at 1/3 of the price of conventional carbon composite solutions. Full process control, sensor integration, and cloud connectivity. A carefully engineered deposition system allows trajectory conformal printing under controlled temperature conditions, combining multiple parts to reach unseen design latitudes in fiber composite processing. 9T Labs hardware and cloud connectivity highlights our philosophy of full process and data control. Fuse parts by applying pressure and heat to get superior surface finish, get maximum adhesion and low porosity, unleashing applications and performance never seen before in composites processing. Join our revolution. Take 3D printing to the next level with 9T Labs.
So now I'm going to take over. I hope you have now a good idea after the introduction of Martin and the short video of how AFT works as a full stack solution. And now let's go a bit beyond the current applications and what we are looking into already now at 9T Labs to really tap into a bigger pool of applications. And this is what we call hybrid manufacturing. So it's really kind of beyond AFT, and it's how to allow actually strong added value for many applications for real serial production. And here it's really about, of course, looking into the finer properties. So what do we need? I mean, in serial parts production, we often need performance. Performance means, of course, mechanical performances, structural performances, but also cost performances. That's always the balance we are confronted with, we are challenged with. And of course, on the mechanical side, there is some hiccups. If you only print and consolidate, you still have the topics of torsion and shear, which is not always solved with the designs. Surface finish is a big argument also, of course, in many different final parts. The small feature details, which can not be brought with a printer, especially if you want to post-consolidate. It has sometimes some challenges, and all in all, cost reduction. I mean, a printer, as we have seen, is very high resolution. It's great to place the material where we need it, but it's also currently still a slow process compared to injection molding on the other side of the scale of process speed. So here we thought, okay, what about just using the printer for where it's best, really printing very precise preforms, placing the fiber along the load path, but then tapping into other technologies we know from composites manufacturing, which would be organosheets if you need to bring a big surface and basically maybe to get some torsion and shear benefits, or just overmold with sheet molding compound, BMC, and so on, to first be very fast in adding short fiber material, which is still structurally interesting, but also using recycled materials, because you get a lot of those chips out of waste from classic traditional processes in composites. And of course, you can also over-inject such preforms if you want to locally reinforce some bigger parts. And in this case, of course, you do put those preforms in those injection molding forms, and you can bring then your paired material basically to run a very, let's say, a new class of parts. And here, what I would like to do, as Martin was saying, is really go into two very precise examples, two parts we have developed and which we can show, and step by step show how with AFT combined also with other materials and technologies, we can really tap into all the challenges which are currently given for those parts, which were actually in metal. So both parts are currently aluminium, so the benchmark is aluminium, and the goal is to challenge them with composites. So first example, here we speak about motorbike application. So especially a motorbike rear suspension rocker arm. So we see here already on this motorbike several parts we have tried or we are producing in-house. And one of them, which is shown on the left, is this rocker arm, which has basically 3 anchor points and allows the movement of the back wheel. So here our approach, coming back to this digital prototyping loop, which is kind of the digital environment, is step by step, really, we get original design. So that's something we get from the customer. And we get, of course, some boundary conditions, load cases, maybe the design freedom, volume, and so on. And based on that, we go into topology optimization. Currently, we often do isotropic. Of course, we are looking into anisotropic topology optimization. And we also do some co-developments here with partners. However, isotropic topology optimization already gives us a really great framework, a skeleton, where we can then in step number 3, when we use our Fibrify design software, place the material along the load path. So that's really the goal out of this topology optimization, is to understand where are the core load passes and then place the continuous fiber really exactly where those maximum loads are. And of course, where we don't need the continuous fibers, then it's about thinking what is the best possible way to, of course, get to the final geometry with different other sets of materials. Could be the neat filament from the printer or the chopped fiber filament, but could also be overmolding or adding an organosheet. In this case, we will see that it's about adding an organosheet. Once we have set up a first design, we go into structural simulation, and between steps 3 and 4, we iterate. So that's the great advantage here. We can iterate very quickly. If we see that in the structural simulation, we have some weak points, we can still add some material at a certain point, rerun the simulation up to a validated optimum stage, which then we would generate a G-code, and the G-code is something which is frozen, sent to the printer, and the printer will replicate this code into a real part as much as we want. So basically moving into serial part production. So we see on step 5, the final design. So what does it mean? I mean, basically this part, the rocker arm, has definitely some torsion load. And obviously, if you only join these 2 loops, which are around these 2 loops of continuous fibers, as you see on the bottom right graphic, and those are connecting basically the three connecting elements to the motorbike. It's not enough, obviously, to cope with the shear loads, with the torsion. So here, the topic in the design was how to bring this extra material, basically how to bring these organosheets into the parts to withstand our peaks or peak loads in torsion. We did some iterations, and we found out that we will place at certain locations of the stack those 090 unidirectional organosheets and combine them with printed preforms. So you see the printed preforms have already a stacked design, so they are not the same at each layer from the layer point of view, but then we even add organosheets within the final stack. So how does it look like? Basically, when we come out of the printer and also the organosheet, all those parts are 2D. They are flat, isn't it? So that's also what is very interesting when we develop the final part in the digital environment. We can project from 2D to 3D and already, of course, take into consideration how to place the fiber for the final reshaped part, because this obviously will create some inner stresses, and we have to know about it in order to already decrease these potential inner stresses, which will either way be able to kind of cure out of the part in the post process. And you see actually here we have very interesting parts. So we go from flat, we reshape it by quite a bit. I mean, you see it's bent on the right side. It's quite some reshaping, while obviously co-consolidating both all our printed layups with the organosheets, and also co-consolidating or integrating those metallic inserts, so that the part, as shown on the top left, is really coming out of the post-process, of the molding process, like shown here. So very good surface finish. We might need some tumbling for the edges, but no milling, nothing on this part. So we are ready to go. What is the advantage here? Obviously, we were challenged by the customer also on the business case versus the benchmark. So here we could prove for a volume of 8,000 parts per year, which was a production scenario given to us, that we could reduce production costs by 37%. The weight reduction obviously is there because of the density of the material, while maintaining the same performance. I mean, we don't need to overperform, but we need to be on par with the current performance of the aluminium parts. So this is also an exercise we do a lot with the customers, going into cost modeling and really looking deep into where will we come out at cost per part. Another example now in the aerospace field, and there's quite a lot of people from the aerospace companies here today in the call, in the webinar. So here we speak about overhead bins. So where you put your luggage in the plane, there is all those bins, and there's this pin bracket, which is basically allowing the movement and of course holding this overhead bins. So this is an interesting part. I mean, there's plenty of those brackets in the plane. One of these application I would like to show you in detail here, because that's also another approach of hybrid manufacturing. Because at the end, of course, you could print, like for the helicopter door hinge, Martin has shown before, you could print different parts, maybe 3 different parts, and interlock them, co-consolidate, but that would still be more expensive than the approach here. So here the goal is how to really fine-tune the design to print a preform, which really makes a difference in terms of structural integrity of the part at the end, while using faster, cheaper processes and also input materials. So here we speak about using BMCs. So those chips are actually really coming from material waste, from other composite processes, so that we can already tap into kind of recycling of materials. So we give them a second life while bringing them into structural applications. But now you will ask, how is it possible with it very simple 2D preform to actually withstand 3D loads? And here, when you look into the digital design, and that's also what we will prove, and we are writing a bigger paper on that to be published in a few weeks, is so we can show also real data, and we will cut parts, etc. But that's what we see in the first experiments, and what we simulated is before molding, we place this preform flat in the mold, and then through the molding process, we actually steer some of the preform into the 3rd dimension, so that we can really carry load from the XY plane to the Z direction into the entire part, and then withstand, of course, the final loads. What is also interesting here is actually we have only 20% of the material is printed. So let's say maybe high value, high resolution, and 80% is this recycled, shorter fiber material, which obviously is, I think, a nice split, so that we have also a way to control the costs of the final part. And here again, what does it mean? I mean, we are able to reduce the production cost by 50% compared to the benchmark. So we are always benchmarking against aluminum here. We have a 45% weight reduction. And of course, we have to cope with the same load case. So the mechanical performance is similar and will also be published in the paper. And here the production scenario is higher because there's really a lot of the small parts in the plane. To summarize a bit after these two examples, what actually is our interest, or the interest of our customers, to go into this hybrid approach. And here really showing hybrid with organosheets, BMC and over injection. There could be, of course, other examples of hybrid manufacturing, but what actually is the extra benefits by doing this? And obviously with organosheets, the main benefit is really to go for the torsion and shear benefits. So this is where, when we see this kind of loads, we tend to always think from the toolbox, let's get into including some organosheets. Cost reduction is also valid because it's pretty neat. You just have to cut it out, but then it's there. It's way faster than printing. On surface finish and small feature detail, this is not really what we mean to tap when we use organosheets. Then on BMC, obviously torsion and shear benefits are also there because we have more chaotic placement of these shorter fibers. Means we are also basically more isotropic in the volume. Cost reduction is great because, as I said, I mean, we can really also use recycled materials. Waste material means here the input material can be way cheaper while being high quality. Surface finish and small feature detail is not the main target here. And last but not least, on over injection, obviously this is going to be neat material or shorter fiber material. So not something too much for the structural topic, but on the cost reduction, it's really great because you can just fill the volume very quickly. Of course, you need high volumes. That is also worth basically handling all the tooling topics and the investments. But when you have the volumes, it's a really great way to over inject the preforms. So to mix mechanical structural properties with the speed and then also the cost competitiveness. Surface finish is great. I mean, you get similar surface finish than usual over injection, of course. And last but not least, you also have the small feature details, which you can really bring into this kind of over injection process. So all this allows us to go in very different markets. So that's also something which is nice. I mean, we screened over 300 applications over the last few years, and we also have a good idea where there is a good fit, where there is no fit at all, which is important, and where there is also place for our technological roadmap. So in aerospace, obviously, a lot of those smaller, intricate parts, which will be brackets, hinges, and so on. But yeah, also going to the turbine, maybe blades, struts, because we can reshape parts, which is then also interesting. In the medical field, we tap into very different properties, as Martin was showing at the beginning with our kind of toolbox of thermoplastic properties. And here it's about X-ray radiolucency in surgical instruments, for example. It's also about dilatation, because you need to obviously sterilize those materials or these parts. So they need to keep their tolerances, very tight tolerances, while being reused. And we could also speak about implants longer term. Of course, aerospace and medical, what is actually similar to these two markets is that they are regulated, highly regulated, takes more time to get in. So we are, of course, doing projects here to step by step go into certification or understanding how to certify a new process for these markets. In the meantime, where we can go faster into market and prove the points which we are claiming is then premium automotive. I would say the automotive market in general is probably a bit too much high volume for now, at this point of time. And of course, all the markets which are leisure, luxury, very interesting because very fast development cycles. It's about quality, but they are self-regulated. So you can go to market way faster while proving that the claims are right, that we can, yes, we can do a few thousand parts in a certain kind of quality for certain costs. So to summarize, basically, what is the advantage to use such advanced manufacturing technologies? And of course, it needs to be assessed on a case-by-case topic. So really, if you give us a specific application, we are able to make feasibility judgment on it, both economical and technical, obviously, to really see if we can bring added value. But all in all, by also putting our engineering knowledge into that, we are really looking to combine these different suite elements, which are cost competitiveness, lightweighting, which is very important, most of the applications, because the high performance we expect to be at the structure level, the process speed, so combining digital development, validation with advanced manufacturing technologies. Of course, because we are developing a new technology standard, we need to look into the sustainability topic, both from the feedstock side, the processing, so be near to end shape, basically don't waste material, and also think about how to recycle those parts which we are producing. So over the entire loop, basically over the entire life cycle. So all these pillars can be combined, and we are really happy if you can challenge us with some of your applications. So at this point, I would give back the microphone to our presenter or moderator, and I'm happy to answer, we are happy to answer your questions. Thank you so much.